Welcome to Safety is Everywhere YouTube channel. Dear friends, don't forget to subscribe this channel and share the link with your safety professional friends.
Hello everybody, we are continuing quantification of basic events. Today we will see the repairable unit. For a repairable component case, there will be two processes. One is failure process, that is repair to failure process. Another one is once the item is failed or component is failed, it is to be repaired, that is failure to repair process. So, the in a repairable unit there will be two process. One is suppose the component starts working, after certain amount of time spent it fails, then it will be repaired. So, that means one is the failure process, another one is the repair process, and we are writing this at that failure, repair to failure and failure to repair process. So, we have already seen the first part, that is repair to failure process in terms of non repairable unit, and we have defined the distributions, different parameters, their distributions, and then how to estimate the parameters with the assuming certain probability models or probability distributions. Now, today particularly in this lecture we will see that the failure to repair process, that means what is the repair process, it is similar to repair to failure process. So, the analogy also we will see, at the same time we will define some of the parameters in this lecture, which is particularly for repair, not for the combined failure to failure and repair, it is the particularly for repair process. So, the content is one is the repairable unit, we will revisit it again, and then the repair distribution, repair density, repair rate, all those may be analogous to failure distribution, failure density and failure rate. And then we will discuss a hypothetical example how to compute all those parameters, and also we will discuss mean time to repair. Okay. And we are primarily following the book written by Komamoto, H and Henley E. J. Probabilistic Risk Assessment and Management for Engineer and Scientists. So, if you do not have this book, please have this book and go through the relevant pages, and I am sure you will be able to understand it even if you do not fully understand in this class, but I will try my best to make you understand. So, as I told you, the behavior of time in of a repairable system will not only depend its lifetime and failure mode, but also on the way the subject can be recovered and the duration of the recovery time. That means, here the object can be recovered, mean the component can be repaired, and the what is the that repair time, that also important here. And the dynamic behavior of the repairable system can be represented as an alternating of periods spent in the up and down state. What is up? Up means working, and what is down? Down means it is under repair. So, there are two state, up state and down state. Up state means it is the working state, down mean repair state. So, for the sake of simplicity, we will concentrate on downtime only. As I told you that in this lecture, we will be interested only in repair process. So, suppose the thing is like that, suppose the component start working here and after time t it fails, then this is the repair time. So, we will be interested in this, not this working part. And what happened, that is why we will assume that the component failed at time t equal to 0. If it is, and it may not be. So, what we will do basically, we will shift the origin to here, we start here t equal to 0, that is the assumption. Okay. So, as if we are concentrating only on a failed only on a failed item or failed component we are doing repair, and we are basically interested to know the several characteristics, several parameters of that process, that means from start of repair to end of repair, the completion. Now, we will generate a random variable which will be the time between start of repair to end of repair, which will be time to repair, time to repair. Okay. This is known to you, I have discussed earlier. We said that the component will be either at the normal state or failure states. So, if it is in normal state, it will continue at the normal state, or it basically there will be transition from normal state to fail state. When it is in fail state, then it continue to be in fail state, and once it is repaired, it will go to normal state. Okay, so then two state system. So, this is over in on the time axis given like this. Component is up means it is basically normal state. So, this is the time when it fails, and then it is the repair time or failure time. So, how long it is under fail state. So, again it is up. So, normal time, again it is failed, and this is the repair time, and in this process this is the combined process going on. So, in the non repairable unit or only that only the failure process case, we have denoted x is the random variable which basically talks about the probability that the component will that component time to failure, and then here we are defining another random variable y, which is time to repair. Okay. So, what is the content of today's lecture? We are interested in this similarly like this, we are interested in y, and we want to find out several parameters related to y, distributions, all those things, and y is basically time to repair, it is a random variable. So, now let us define formally some of the parameters. Okay. So, as I told you, y is a random variable defined over the positive real number, indicates the downtime of a repairable unit. Downtime means the total repairable time, and that is nothing but the time to repair, the span of time from failure to repair completion. It fails and then start repairing, and when repair is completed, it will go back to normal state, that time is TTR. So, now what we will define here, first we will define the cumulative distribution function GYT, that is cumulative distribution function of repair. So, what is our GYT? That is basically repair distribution. What it is? It basically represents the probability that a unit whose restoration process starts at t equal to 0 will be repaired before time t. Okay, so, that means this is probability y, the time to repair, less than equal to t. So, if you recall the failure distribution, there we we have used failure distribution f x t, and we say this is cumulative failure distribution or failure distribution. We say that probability that the component will fail or x less than equal to t within time t. Here we are concentrating on the repair process. So, what is the probability that the component will be repaired within time t is GYT, capital GYT, that is what is written here. So, our first concept is repair distribution. Now, suppose what happened at time t equal to 0, there are n number of capital N number of identical component under failed state, and you started repairing them from t equal to 0, you start, and then maybe after time t you found out that MT this is the number of component completed repairs within time t. Okay. So, this MT is nothing but the number of component repaired within time t. Then what will be the repair distribution? Repair distribution is number of component completed repaired by total number of component under repair at time t equal to 0. So, that GYD, this is the from probability concept, this is also probability, but when you have the data you are able to find out the values. Okay. So, this is the way we will basically compute the repair distribution or repair probability. Now, this cumulative distribution function, when you take derivative of it, then you will get density function, that is what you have seen earlier in failure distribution. We have seen earlier f x t, and then we say that there is small f x t which is d by dx f x t, capital F x t. So, the derivative of, if this is the cumulative distribution, this is your density function. Okay. You can go from the basic fundamental of density function, mean what is density, but from the histogram also, but those things we have discussed earlier. So, also we have discussed that if you know the cumulative distribution function, then you will be able to find out the density function by taking the derivative of it over time. So, that is why here from the repair distribution to repair density function. So, what is the repair density function? Repair density function, repair density function. Repair density function small g y t equal to d by dt g y t by dt. This is this is t also. Okay. So, this is our formula. Now, this can be written in this manner. Then what is this value g y t into dt? This is basically talking about that probability that the component will be repaired in between t and t plus dt within this small del dt time, the probability that component will be repaired. So, this is density, this is the time interval, density multiplied by time interval will give you the probability, and it basically talks about within a small interval and time what is the probability that a component will be repaired. Okay. So, now this one can be written in this form also. If I know the density, I also know the distribution. That means, what is the cumulative distribution if you know the density? It is the integration of density. So, that is what you have written here. So, g y capital G y t equal to 0 to t small g y u d u. So, and if you take integration here, it will be g t, right hand side will be g t. Now, again this one, if I have two different times, the t 1 and t 2 in between, what is the probability that the component will be repaired between t 1 and t 2, then you also can find out from this equation. You integrate in between t 1 and t 2 g y d y. So, suppose if I say my repair distribution is this, that is GYT, I take two values, that is T1 and this one is T2. So, what is the probability that component will be repaired within this T1 and T2? It is the area under this curve in between T1 and T2, that is what you are writing. Suppose if I consider that T this my T value is this, then I want to know what is the probability the component will be repaired within time T, then that is nothing but GYT, and this is the integration of under this equation the area under the curve from 0 to T. So, that is what we have seen the same thing in failure distribution case. Now, in repair distribution we are seeing the similar thing. So, they are same, only the difference is one talking about time to failure, another one today's one talking about time to repair. Okay. I hope that you got it. So, what you learn now? Repair distribution, repair density function and their relation, and we are considering only the repair process and with certain assumptions already given to you. We will now go to repair rate, from repair density to repair rate. Okay. So, repair density you have already seen that d by dt into GYT, this can be written like this, GYT plus delta minus GYT by delta. Okay. So, now GYT plus delta minus GYT, if I write in terms of M, what is M? Number of units repaired within T plus delta, then G T plus delta will be M T plus delta by capital N, because capital N is the number of units under repaired at time t equal to 0. Similarly, GYT will be M T by N, then the resultant quantity will be like this. So, if you at t equal to 0, there are M component failed component under repaired, and at t equal to t plus delta, M t plus delta is repaired, and at t equal to t, M t components are repaired, then the difference M t plus delta minus M t, this is nothing but the number of components repaired within delta amount of time. Okay. So, and divided by if you put divided by n, then see that will be the proportion of component which is repaired by time delta, and if I want it unit time, in unit time, then you have to divide it by delta, and that is what is the density. So, repair density in terms of experimental data. It is again, if you have found out this one in failure density also. So, if you recall the failure density, what we have written there? We have written f x t equal to, we have written n t plus delta minus n t divided by capital N into delta. This you have seen earlier lecture. Okay. So, all of you know n is total number of units, M t is number completed repairs before time t plus delta, and the difference by this the proportion of unit expected to repair within this time, which is this. In other way, when we actually go in terms of probability, we say that probability that the failed component will be repaired within this time t. And when you have experimental data, we have computing in this manner. Okay. So, this is basically repair density explained. Now, we go to repair rate. What is the repair rate? Repair rate is that probability repair rate, the probability that the unit is repaired per unit time. Please remember, unit is repaired per unit time at time t, given that the unit is failed up to time at time 0 and has been failed up to time t. Means suppose this is my repair at the time t equal to 0, the component fails, and this is time t equal to t. Till now the component, suppose this is my down time and this is my up time, till now the component is here. Now, what we want basically, what is that it will be repaired, immediately, instantly after time t. So, that ratio is talks about, I mean there are, this is a conditional one, that means up to time t it is under failed, not repair, it is in the failed state, and at time it will be repaired. What is the what is that quantity? This quantity is is denoted by our repair rate. So, it is similar to failure rate. In failure rate, what we have considered, that the component is working at time 0 and it is working time till time t equal to 0, but what is the probability that it will be failed immediately after that? That means instantaneous failure, and there what happened, we consider that the failure conditional to survival up to time t. Here also repair conditional to that the system is at failed up to time t. So, the same way it is written here. If now let me go back again for that failure rate, because you have seen this one earlier, failure rate R x t. There what we say, that we say f x t by R x t. What R x t? R x t 1 minus f x t. Here the equivalence is capital F x t's equivalence is g y t, and small f x t's equivalence is small g y t. I hope that you understand now that what is the, that within this very small amount of time, let it be delta time, it will be or otherwise in that per unit time, it will be per unit time, it will be repaired. Okay. So, this is an important concept for all of us. Now, we will see that as we have the repair process, our sole purpose here is to repair as quickly as possible, and the parameter of the repair process, which basically talks about what is the performance of that repair process, is MTTR, mean time to repair. So, now mean time to repair will be computed using this formula, that means T g y t dt 0 to infinite, T changing from 0 to infinite. Now, when this time is infinite, suppose I given a failed component, you are given infinite, a very large, extremely large amount of time, what is the probability that it will be repaired? It will be repaired, it is with one probability. So, then if this is the condition, when t equal to infinite, then your mean time to repair is will be with this formula. Okay, 1 minus g y t dt. Fine. So, I hope that you got the idea of repair process. Repair process means it component failed and you start repairing it. Now, time to repair is the random variable, which is the positive quantity, and that follows certain distribution definitely, and we have tried to find out all those distribution. First, the repair distribution, that means the component will be repaired within time t. Then we have seen the repair density, and then we have gone for repair rate, and finally, we have seen that what is the performance measure in terms of mean time to repair. Okay. I hope that you have understood all those things, because it is similar to failure distribution. Okay. So, let us now see one small example, that how we will make all those distributions. Let us see. Suppose we have 15 identical components, create a timeline t here, and this side time t equal to, let it be 0, all 15 failed. Now, your repair starts. Consider that the repair process is similar for all the identical components. Now, the first one will be repaired. First one, this is the first one, it will be repaired maybe by 4.1 time unit. Second one 5.2, third one 6.3, fourth one 0.8. So, like this, if I go for the 14th one 5.8, 14th one, and 15th one is 0.05, 0.5, not 0.05, 15th one. Okay. So, this is what is the, suppose you have done this experiment, 15 identical component you have considered, at time t equal to 0, everything has gone to, every component gone to identical repair process, and then you found out that this is the distribution. So, now we want to, with this data we want to find out what will be the GT value, that the repair distribution, repair density and repair rate. So, repair distribution, repair density, repair rate. So, as the TTR values are known, so we added here 0 also, because at time 0, anyhow, let us consider from here we just found out this TTR values, we arrange in ascending order. So, first 0, then followed by we have written 0.5, because this is the one component which is repaired within this time. Then the next smallest unit is what? We have written 1.1. Okay. So, number of units repaired 1 and 1 I have written 2. So, is there any other value? 0.8? Yes, 0.8 is there. Okay. So, if I arrange them in ascending order, that means from 0 to the maximum one will be, I think, some value 6.3. So, you will get 6.3. Okay. Now, what happened? We have created TTR. This is also time to repair for individual component. We are created a general TTR, time to repair, where we started with 0 and then we have given 0.5 increment. So, 0 to 0.5, 1, 1.5, 2, like this. So, I can say let the delta is 0.5, that way we have created. Then what we are finding out, that how many component repaired at each of the, each of the time. Now, if I want to know what is the amount repaired at time t equal to 0, it is 0, but number of component repaired at time 0.5, we found that one component is repaired. So, we have written 1. So, number of component repaired by 1 unit of time, that we found that 0.5 and 0.8, it is 2. Similarly, from 1.5, so that means these 2 plus 1.1 and 1.2, they are less than 1.5. So, 4 units, like within 5 units. Similarly, within 6.5 units of time, all 50 units are repaired. Okay. So, this is basically MT means cumulative number of repair. So, within time 6.5 unit, all 15 components have been repaired here. We have not considered that in something not repaired, we consider all put under test repair, put under repair is repaired. Then your repair distribution is MT by N, this one, and this is basically 0, N is what? N is 15, then 0.7 like this is 1. What will be the GT values? GT values will be that this minus this, G small g y t. What we found out? M t plus delta minus M t by delta into N, or we have found out G t plus delta minus G t by delta. Okay. So, M t plus delta by N, that is G delta by S. So, now using the formula, or if you want more conventional way of learning. So, you just see I have already given to you, sorry what is happening, you see M t plus delta minus M t by N into delta. So, this formula you use here and you will be getting G t values, and then M t values will be G t by 1 minus this. So, this will give you this values. So, now you can plot. If you plot, what happened? This side t and this side your G t, this side may be small g t, this side small m t, you will get different plots. Now, this value G t 0, 0.7, 0.13 like this, it is up to 1. So, first when t equal to 0 it is 0, when t equal to 0.5 it is basically 0.07, and when then 0.8, 0.13 or some curve like this you will be getting, that is G t. And similarly, small this one also you plot, you will be getting some other type of curve, and hazard rate here it is basically repair rate, you will get repair rate, equivalence failure rate, the similar curve you will be getting. Is it constant? No, here it is changing. Okay. So, you definitely have understood this, and then another issue, that how to compute the mean time to repair from this data. How do you compute mean time to failure from this data? Same manner you compute. What is there? What is the formula for MTTR? Integration T G T dt, 0 to infinite. Now, you see what we have done here. What is the dt value? Everywhere I said that the difference is 0.5. So, that is your dt or delta values. Then what will be the t values? T values will be the in between. So, here 0.25, first one 0.25, 1.25, sorry 1 and 0.5, that is 0.75. So, similarly, last one 6 and 6 plus 6.5 by 2, 6.25, and what is the GT values? GT values are there. For first one it is 0.13, second one again 13, and the last one 0.27. And what is the dt value? Dt value or delta value equal for all the cases t values. So, that is why we have multiplied finally this one, and you are getting these values. This is what mean time to repair. On an average, if a component is failed, then on an average a failed component will be repaired by this unit of time. This is average time. Okay. Now, summary. You have seen this summary related to time to failure data, now time to repair data. So, once you have data, you develop histogram, then through polynomial approximation you can find out GXT, and once you know GXT, the other distribution you will be able to find out. You will be able to repair distribution, you will be able to find out repair rate, you will be able to find out mean time to repair. And we have given you in reference to time to failure data how the exponential and Weibull distribution is used. So, here also you have to find out what is the appropriate distribution. For repair process, many times we use log normal distribution. So, that means time to data if follows log normal distribution, that is another path. You find the assumptions, estimate the parameter, then you get this, again you find out all other things, and the most fundamental formulas are given here. These are the most fundamental formulas, and these formulas if you compare with the failure process formulas, only failure process, then you will find out one to one analogy there. So, it is very easy to remember, that is why. Okay. So, now what happened, we will move to the combined one, that means one failure process, one repair process. If we combine the two, then that is the most general one, that is the repairable unit case. A repairable unit, once it fails, it will go through repair process, then it will work till failure, that is the failure process. So, these two processes will be combined, and we will be telling that is combined process, which is most aptly fit for the repairable component or repairable system failure analysis. References are already told to you. Thank you. I hope you have understood it.